So yeah, we will discuss first about this lecture 11 about detection and segmentation and so on. So probably you guys understood this slide of so the here the story in this, the main story about this lecture is that so those tasks about object detection and also especially this instance segmentation needs the classification label or some prediction output corresponding to each pixel, which means that we need the same number of output as the total number of pixels that we have. So in that case, we just applied the conv layers without reducing the spatial resolutions. So we do not involve any max pooling, right? And then we just impose a proper size of proper padding size, so that we just maintain the total number of width and height, right? But in this case, this will this is not actually this is not frequently used because it produces a lot of large size of an activation value. So if you remember the VGGNet, I think I explained it already, but so in this case, you have to closely understand this pattern in terms of their size of the activation map and also the number of parameters as we go through these layers. And then the activation map at the first layer come as an output. That is the largest activation map size throughout the entire network architectures in this VGGNet. So it is it amounts to like 3 millions of activation map size, right? And why is it so? It is because we didn't reduce the spatial resolution at all, but we used the 64 number of filters. So this 64, which is a lot larger than this 3, so that way our activation map size got bigger by the ratio of, by the amount of this number of convolution filters. Okay, so in this case we usually in order to avoid this really significant increase in terms of this activation map size, we just gradually reduce the spatial resolution through this max pooling, and then we also gradually add the number of channels by adding or using more number of filters, right? So if we just remove the max pooling in this entire stage, and then we first use 64 filters and 128 and 256 filters, so that we can cover complicated patterns through various different combinations of the previous layers activation the filter patterns, right? So in that case the activation map size around around the middle layer in our conv, and then if we use more number of filters, and then the activation map size will significantly be large than the input one. So we will easily get the out of memory error, right? So this is not a practically useful solution. So instead we use this kind of bottleneck kind of structure. So in this case, we want the same number of we want the output that has the same same spatial resolution or spatial size as an input, but in this case we just use the max pooling so that we can properly like maintain not kind of a big size of the activation map in the middle. And then yeah, from here, yeah, we just increase the spatial resolutions so that we obtain this same size of an input, that's the spatial size of the input image. Okay, so in this case, yeah, especially this part, yeah, so and also this part is called the encoder, encoder, and this part, the latter half, is called the decoder, because we can view the first half as encoding some meaningful information out of the entire image, right? Just like extracting out some meaningful features through our convolution filters, but the latter part is like utilizing those meaningful information extracted or encoded from our image. We actually decode it into the output that we want. I mean, yeah, in the form of our output, whether it is a pixel-wise label among the predefined categories, or maybe some instance segment. In the case of an instance segmentation, it will be, yeah, it will be like, yeah, binary classification label, whether it is a foreground or background pixel, right? In the case of an instance segmentation, the pixel-wise label is either 1 or 0, depending on whether that pixel is, yeah, belonging to the particular object of an interest, right? And sometimes, yeah, in the case of, yeah, image level classification, image translation case, yeah, which we will study in probably in the next lecture, based on this generative adversarial network. And then, yeah, that will just produce the output in the form of RGB color values. So, although I will show this example later, but just to give you some interest. So we want this kind of a task. So although it is shown in a video, but you can just think of each frame as a separate image, okay? And so each separate image is given to our network, and then it will exactly go through this kind of neural net architecture, which encodes the input image into much smaller spatial size of an activation map. Although the depths will become, yeah, thicker and thicker, or larger and larger, so that we can encode more, various different useful or meaningful patterns. And then once we encoded those meaningful information, and then we now turn to the decoding phase, so that we obtain the final output that has the same resolution, spatial resolution, as the input. But in this particular case, the input is the image on the left, and the output is also another image on the right. So in the case of this output, it is not just a classification label for each pixel, it is just an RGB value. So in that case, our number of channels at the end as a final output will be just 3 channels, which is exactly the same as input channels of RGB. Okay, so that will also go through this encoder and decoder network. Okay, so in this case, yeah, in this lecture, we want to study how to implement, or how we design this decoder network, which just increase the number, increase the spatial size. Okay. So to that end, we just, yeah, we sometimes use this unpooling, like a max unpooling, yeah, and also deconvolution and so on, right? So at a high level, those unpooling and deconvolution plays a role of increasing, yeah, the spatial resolution of an input. Okay. Okay, so Given this, if we do the unpooling, yeah, we can obtain this, right, by just copying those values into a larger pixel. So one pixel is becoming 2 by 2 pixels of having of the same value, right? So that's the idea of this unpooling, right? And so related to this, although it is not directly, it may not be directly related, but I feel it is, it has something in common with what we studied before in this inception module. So let's see. So this is the inception module version 2, and I want to focus on this part, 3 by 3 max pooling, right? So in this case, if we apply the max pooling, and then the spatial resolution should be reduced by the ratio of this max pooling filter size, right? But in this case, we were able to maintain the same number of spatial resolution. And how did we do that? So what was the main idea here? So here, so max pooling is one way of computing one single output out of some size of window, right? And then if we apply the stride size as 3, and then it will produce like a single value per 3 different pixels, right? So that's how we downsample, or how we reduce the size of an image, right? But in this case, we just apply the window, the filter size. Filter size is 3 by 3, but the stride size was what? Stride size is 1, right? So that was part of the previous, the midterm exam, right? So if you studied this part, then I think you guys will remember. So in this case, the stride size is 1, right? And then what should be the padding size? To maintain the same input and output activation maps. The size. So it's exactly like the conv, right? So if we apply the 3 by 3 conv, and then in order to make the same spatial resolution, we need stride size as 1, and also the padding size as also 1, right? So here the stride size is 1 and the padding size should be 1 to obtain this. Okay, then let me change it as a 5 by 5 pooling, and then to have the same size of an output in terms of a spatial resolution, what should be the stride size, or the step size should be? Step size should be. If it was just a convolution with the filter size of 5 by 5, what would be the step size that we need to obtain the same size of a spatial resolution? It should be 1, right? It should be 1. What about the padding size then? Padding size 2, right? So it's exactly the same. So max pooling is, in terms of the number of an input that we need when applying the particular window at a particular position, and then in terms of the number of pixels that we need, and also the number of output value that we produce, okay? Between these two, the relationship will exactly be the same as the conv, right? But the operation is just a max max operation instead of just a linear combination. 이거 이해 가죠? 다 알고 있죠? 뭔가 알면 좀 표정을 밝게 해주면 내가 좀 알아차리는데 좀 도움이 되지 않을까 싶어요. 포카 페이스를 하고 있으니. 네. 포카 페이스를 하고 있으면 포카를 쳐야죠. 네. Okay, so in this case, if we do the max pooling with the overlapping windows as a stride size as 1, and then what was the result? So like, yeah, I think I have some examples before, but 1, 2, 5, 3, and 6, and 8, and maybe -1 and 0. So in this case, if we do the max pooling over here, and then it will produce 5, right? And then if we do this max pooling, and then it will produce 8, right? And then when applying it to here, it will also produce 8. And then like this, so if we have a 2 and 1, and then it will also produce 8, and then also produce 8, right? So it's like duplicating or copying this 8 into like nearby pixels, right? So that was the effect of applying the max pooling with an overlapping windows, right? Okay, so in this case, it is somewhat similar, I feel, because if you just think of like this as a max pooling output from some 2x2, 2x2 activation map, and then somewhere within this window, the max value would have been 1 and 0 and -1 and maybe -2, and then this would be picked as this guy, right? But if we just recover this into 2x2 pixels, we don't know what are the other values, right? So in that case, we just assume that this one was just one appeared, repetitively in all each of the pixels in our windows, right? Okay, so that way it's like duplicating or copying this max value. I mean, max value means that this output was the output of or result resulting from the max pooling layer. And then if we do if we imagine the inverse operation, and then it is just copying this max value into all the pixels within that window. Okay, so that was a simple idea of this unpooling. And also there is a max unpooling, which also was discussed in the next lecture when doing the guided backprop and similar kind of things. So in this case, so we assume this kind of symmetry, symmetry in terms of like this inverse operation of the input and output activation map size, although they will involve the different sets of parameters. So if we did an max pooling over here during our encoding phase, and then along this 4x4 pixel values, 1, 2, 4, 3, and then if we assume we apply the 2x2 max pooling, and then 4 will be chosen, right, at this particular layer, right? Suppose this one was like 2x2 max pooling, and then in terms of the symmetry, we will do some unpooling at this point or at this particular layer that will increase the spatial resolution into this, right? So in this case, we don't just duplicate this 4 into like these 2x2 patches having the same values, but instead we actually we memorize where this large value came from, like over here, and then so in this case this max value is only only placed in the corresponding position where we memorized as the source or the position that has the max value, and then for the other values we just simply put zeros. Okay, so this is another way of this doing this max unpooling. Okay, and then now we discussed about this transposed conv, or sometimes called deconvolution. So in the case of deconvolution, it can be viewed as the process of inverse operation of this conv, right? So so in the case of conv, so given this 3 by 3 pixels, it can be viewed as producing a single value, right? So we just apply the learnable convolution layer that correspond to the convolution coefficient or linear combination coefficient that we apply in this particular region. And then if we imagine its inverse operation, given a single value, we just generate maybe this 3 by 3 set of value. Okay, so you can view it as like an inverse transformation of this conv. Okay, so before discussing why it is called a transposed conv, but let's just give a high level overview or intuitive understanding of this deconvolution. So so let's think of A, B, C, D, E, F, G, H, I. So these are the pixel values. Okay, so we denote those pixel values as this, and then let's apply the filter as 1, 1, 1 and 0, 0, 0, 0, 0, for example. Okay, so this is one simple example of applying the conv, and then when it was applied at this position, and then it will just produce the linear combination of A, B, C, D, and E, F, and G, H, and I with the corresponding coefficient, right? And then let's suppose its activation value was obtained as 10. Okay, and then it means that at this particular position, the strength of this pattern is corresponding to 10, right? And suppose we apply the same filter maybe over here, and then it produced the activation value as only 3. So in this case, intuitive meaning or meaning of it is that at this particular position in the green window, it showed much strong signal or a strong pattern of this convolution filter that we defined, right? But at this pink part, it only showed the small strength of 3, right? And then here, if we just think of the inverse operation or transformation, suppose I gave you only this strength or this activation value, and then I want to you are asked to reconstruct these pixel values only based on this activation map and also this particular filter pattern. Okay, so in this case it is basically the problem where we cannot obtain the unique solution, because in this case A plus yeah, E plus I should be 10, right? In general, yeah, our filter coefficient is 1 for these A, E, and I, right? And then can we just infer or obtain the exact value from this single equation? I mean, exact value of A through I, for example, right? So we have at least 3 or 9 different variables, but we only have a single equation, and so using only a single equation, we cannot exactly define each of our 9 variables, right? So it's basically impossible to solve the exact value based on this, I mean, for this inverse transformation, right? So one approach that we can simply take is as follows. So we know that we understand this value as like the strength of the filter pattern, right? And then for this part, so let's just simplify so that this part is not overlapping with this green part, okay? So in this case, somewhere we found the activation value as 10, and then for that corresponding part, we can just think of this filter pattern being found as the strength of 10. So for example, we can just reconstruct the original image as this, right? By just simply multiplying this scalar value that corresponds to the strength of that filter pattern, and also applying it element-wise with our filter pattern. And somewhere over here, it only showed the activation value as 3, and then we just reconstruct this original image as having only the 3 times this filter pattern. Okay, so this is the main idea of deconvolution. Okay, so again, the main point is that it is impossible to determine our individual variables at a pixel level as a unique value, because it's an underdetermined system, right? So we basically have more number of variables than the number of equations, and so we just take the simple way of just reconstructing this kind of by just doing the scalar multiple with our given filter pattern. So does it make sense? Okay, then let me just show some another example so that I can help you understand a little bit better. So suppose this is our activation map, and then our filter is 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is our filter. And then what will be our deconvolution output? So we have 1 here, and then we just, so it is a really large number, but 9, 10, 11, 12, 13. And then now we have another activation map on the right by just moving 1 pixel to the right? And then we just multiply it, right? And then here we can also define our stride size or the step size. And so if we just assume the step size as 1, and then we just multiply 2 by with this filter pattern, and then we overlap that with 1 pixel right. Okay, and so it's a 10, 12, 14, 16, 18, and so on, right? And then how can we handle these two overlapping values? We just simply take the addition of them, the summation of them. Okay, so this is the main idea of deconvolution. Okay, so let me ask one question over here. So why do we need this deconvolution? I mean, what's the goal or purpose of using this a little bit complicated or heuristically defined layer? It is because we want to increase the spatial resolution, right? So that was the main goal. So in this case, in this case of using the step size as 1, okay, step size as 1, will it increase the spatial resolution? Okay, so in this particular example, so we have 2 by 2, and then what will be the spatial resolution of the output activation map? It is just 4 by 4. Does it make sense? Because for each pixel, it is expanded into 3 by 3 patch, right? And then if we use the step size as 1, right? And then 3 by 3, and then it will be moved how many times? Yeah, with the number of the pixels that we have in the input activation map, right? So originally we have a 3 over here, and then we have a 2 pixel, right? And so we only have one additional row, right? And then if we have maybe n by n, and then the filter size is maybe m by m, what would be the spatial resolution? So it is just an n, and then yeah, we can exactly do the inverse operation, computation of zero padding. So suppose it is 3, and then given this n original number of pixels, it will just increase one additional pixels on the left, right, and top and bottom, right? So it's like n plus n minus 1 over 2. I mean, yeah, this equation is not that important, but my point is, did it increase the spatial resolution? Although, yeah, it of course increased the spatial resolution, but it increased by the amount of this, right? So if it was maybe 1000 by 1000, and then if it is a 3 by 3, and then what will be the resulting activation map size? It will be just 1002 and 1002, right? So it didn't increase the spatial resolution much, right? So we need some kind of ratio, right? The multiplier, integer type of a multiplier. So if we have a 1000 by 1000, and then we at least want to obtain this 2000 by 2000, which has the ratio of, like, increasing the spatial resolution by the ratio of 2, right? So how can we obtain or increase this spatial resolution in this manner, as this multiplication? So that is true. That is by setting the step size as more than 1. Okay, so if we use the step size as, for example, 2, okay, and then for each pixel, when moving one pixel to the right, by the amount of a single pixel, and then in the output, the step size, if the step size is 2, and then roughly the image size becomes like 2 times larger than the original one, right? So typically in this deconvolution, this step size is set as more than 1 to increase the spatial resolution. So any questions so far? 네.
겹쳐진 부분은 더해진 부분.
합쳐진 부분이요? 네.
공식이 살짝 이해가 안 되는데
네.
위에 예제랑 대입해보면 값이 좀 달라지는
그러네요. 미안해요. 이거 없어야 되네. 이게 하여튼 가운데 거 빼고 나누기 둘 하면 이제 한쪽으로 삐져나가는 그거잖아요. 근데 이제 한쪽으로 또 다른 쪽으로도 삐져나가니까 그러네요. Any other questions? Okay, and then
필터를 학습시키는 거.
이거요? 네. 이것도 여기서 보면 이게 러너블 업샘플링이라고 그러잖아요. 이게 결국은 이거 값 하나를 어떻게 그 큰 패치로 할 것이냐. 그리고 이게 지금 오버랩이 되니까 이게 좀 약간 좀 이상해 보이긴 하는데, 만약에 필터 사이즈가 3x3이고 저기 스텝 사이즈도 3이다라 그러면 오버랩이 전혀 없이 한 픽셀이 정확하게 3x3 픽셀이 되고 그 옆에 3x3 픽셀이 탁탁 되는 거예요. 그죠? 근데 저게 이제 트레이너블이라고 불리는 이유는 뭐 당연히 그 앞에 있었던 그 언플링 같은 경우, 맥스 언플링이나 뭐 그 전에 그 복사하는 언플링 같은 경우 그런 식으로 한 픽셀을 그렇게 이제 2x2 혹은 3x3의 이제 그 패치로 이제 사이즈를 키워주긴 했지만 그 프로세스 혹은 그 과정 자체에서는 어떤 트레이너블한 파라미터도 없죠. 그죠? 근데 여기서는 이제 그 파라미터 요 한 픽셀을 여기 이제 3x3 픽셀로 만들어주고는 싶은데 그 3x3의 픽셀로 어떤 값으로 만들어줄지 그거를 역시 학습을 또 하는 거죠. 이건 뭐 네, 그냥 학습은 그냥 또 백프랍에 의해서 또 되긴 돼요. 왜냐하면 이게 다 보면은 여기 값이 뭐냐? 이 1 곱하기 5에 나오는 값이죠. 그래서 저 픽셀 값에 뭔가 그레디언트가 도달을 했다. 그러면 그건 어찌됐건 이 5와 1의 곱셈으로 이루어지는 픽셀 값이니까, 그러니까 그레디언트가 각각 다 흐르는 거죠. 기본적인 이 선형결합 혹은 이제 리니어 컨비네이션이라는 요소는 변하지 않았기 때문에. Any other questions? Okay, so let's discuss why it is called a transposed conv. Okay, so we now understand this process as the inverse process of convolution, and that way we can kind of understand, we can call it as deconvolution, because d something is referring to the inverse process of the original process. So in order to understand that, we need something related to the linear algebra. And so this is a simplified or simple example of a 1D convolution. So this is an activation map, and this is our filter. And when applying the deconv, and also the step size as, so what's the step size over here? The step size is currently 2, right? Because A is multiplied with this vector, and then for the second value, that is 1 pixel, 1 pixel to the bottom, and then we multiply the filter, and then in the output activation map, how many pixels did we move? Only, we moved 2 pixels in this case, right? So roughly, it is like upsampling, having the ratio of 2, right? It increases the input activation map by the ratio of 2. And for this overlapping part, we simply add them together. Okay, so let's see. So let me just explain this. Okay, so the left part is just a normal or standard conv, and this conv is sometimes computed as the single matrix vector multiplication. So in this case, so there is a typo over here, it should be Z. So in this case, let's assume we applied one-dimensional conv, given the activation map as A, B, C, D. So this is our input activation map. And then we want to apply the filter as X, Y, Z. And then we apply this filter. I mean, here the padding size is set as 1. So in that case, we apply this window for this part. right? And moving one pixel to the bottom, we apply the convolution over here, and over here, and over here, right? So that way, computing this linear combination and then making it as a single one-dimensional vector, this is our output activation map through this one-dimensional convolution. Okay, and then if we were to implement this process, and then we can, the simple way to implement this would be to use a for loop, right? So we iterate through the entire position, each position in our input activation map, and then compute the linear combination at that corresponding patch or location, and then obtain activation map, right? But what if we just make it as a batch processing? So in that case, it is basically a linear, set of different linear combinations. So the first way is, so we have this activation map, input activation map, including these 0, right? And then the first linear combination with this guy and this guy, okay? So that can be represented as the inner product with XYZ and here, right? And then what about the linear combination coefficient for this inner product corresponding to this input activation map? That will be simply set as 0, right? Okay, and then for this second window that we apply our convolution, then we set 0 here, XYZ here, and 0, 0, right? So basically we just slide this filter that has the same size of a vector as an input activation map, including the paddings, okay? And then simply in order to increase the filter size, so we just simply pad all zeros over here, and then we move this pixel using this sliding window kind of idea, right? Okay, so in this case, if we just compute this simple matrix and vector multiplication, and then we can just obtain the activation map using this single operation, right? So in practice, if we implement this guy as a for loop, okay, in the for loop case, when our GPUs are looking at this computation, they will not know how to compute how to parallelize this for loop, okay? But if you just form this big matrix and then define this whole process of convolution as this single matrix vector multiplication, and then it's if we just write our programming code in this form, and then GPU will be able to parallelize this, okay? So in that case, it will be just it will be computed in parallel, which is much faster than this for loop version, okay? Okay, and then there could be another way of this forming this single matrix vector multiplication for this exact same convolution computation. So another way would be to this guy. So here, so we just duplicated or copied our filters as a different rows in our matrix on the left, right? So that way, we just copied our convolution filter coefficient. But how about this? So we have a convolution filter as XYZ, right? And then we have an activation map as 0, A, B, C, D, and 0, right? Including the 0 padding, right? And then what will be the first row that forms the first activation map? It will be this guy, right? 0, A, B, right? And what about the second row? A, B, C, BCD, CD, 0, right? So in that case, this result will be exactly the same as the output, the convolution output. Okay, so in general, yeah, this kind of method is called im2 Kuocw, because we just change it or convert our image, input image, into the column vector. So in this particular case, it is just a row vector, but yeah, if we just do the transpose version, and then we have an XYZ and 0AB and ABC, BCD, CD, 0, right? So that way, out of our image of this ABCD, or including the padding 0, ABCD, and 0, and then we just simply cut those window region or subpart and made our columns to form this entire matrix to be multiplied with our filter coefficient as a single vector. Okay, so that is called the im2 Kuocw method. So I believe so in modern deep learning libraries, if you run the convolution, and then it is internally converting this image into this form, and then just implement this convolution operation as this a single matrix vector multiplication. Okay, instead of just running or iterating through this for loops. Okay, because that way we can utilize the GPU parallelism or acceleration. So in this case, what's the disadvantage of this method? Yeah, compared to the for loop case. So what's the cost? So in this case, we can parallelize this computation, but here the price that we need to pay for is additional memory. So in this case, what was the input activation map? I mean the size of an input activation, including the 0 padding, we only needed a 6 number, right? And then if we just do the for loop and then compute the inner product, or convolution on the corresponding positions, and then we don't need any additional kind of redundancies in terms of storing these numbers. But once we form this into this matrix, and then out of 6 number, we need 3 times 4, which is 12 numbers, right? And simply this A was duplicated, and those were all duplicated in this manner, right? So the single values are duplicated into our memory, and so we require more size of our memory. So that is the main drawback of using this im2 Kuocw, but speed or computation is done much faster. And also this is the same. This has the same drawback. So in this case, what were duplicated? So the duplicated part was not the input image pixels, but the filter coefficient, right? So filter coefficient of XYZ were duplicated. Were copied multiple times. So that way we need more number of memory. Okay, so any questions about it? Okay, and 그러니까 이렇게 하면 이걸 for loop를 하면 주어진 이제 ABCD, 그러니까 0까지 포함한 거 그거 만들어 놓고 이제 XYZ라는 이제 필터 코에피션트 받아서 이제 이걸 이제 컨볼루션을 한다는 거는 이렇게 윈도우를 이렇게 쭉 돌아가면서 이제 하는 거잖아요. 여기서 액티베이션 맵 구하고 또 이렇게 하고, 이거를 이제 저 하나의 그냥 어레이, 원디멘전 어레이에다가 그냥 그 해당 위치 있는 거를 네, 그 리니어 커뮤니케이션 혹은 내적을 계산하면 되는 거죠. 그러니까 저렇게 하면 사실 뭐 저렇게 하는 게 사실 일반적일 수 있어요. 근데 이제 중요한 건 이제 좀 트릭을 쓰면 이런 식으로 이제 한 방에 이제 어떤 매트릭스와 벡터의 멀티플리케이션으로 나타낼 수가 있다는 거고, 이렇게 나타내면 뭐가 좋냐 하면, 이 매트릭스 멀티플리케이션에서 기본적으로 일어나게 되는 거는 여러 번의 내적이에요. 왜 그러냐면 여기서 이거랑 내적되고 또 이거랑 이거 내적되고 이 네 번의 서로 다른 내적이잖아요. 그러면 이제 GPU는 이제 왜 GPU가 딥러닝을 이제 빠르게 계산하느냐? 하여튼 뭔가 매트릭스와 벡터 혹은 매트릭스와 매트릭스도 상관없는데 그런 매트릭스 간의 곱 혹은 매트릭스와 벡터 간의 곱이 딱 들어왔다. 그럼 걔를 하여튼 이런 식으로 지금 여기서 이제 이렇게 한 줄로 쓰여진 뭐 맷머리니 뭐 이런 거 쓰면 되는 뭐 이런 한 줄로 계산되어지는 거를 내부적으로 싹 다 패러렐라이즈를 해요. 지금 무슨 소리냐면 이 GPU가 갖고 있는 수백 수천 개의 코어에다가 이제 이런 것들을 쫙 이제 4개 서로 다른 코어들에다 딱 할당을 해갖고 이제 그 4번의 이제 계산을 시퀀셜하게 하면 뭐 시간이 4배 걸릴 걸 이거 시간을 4분의 1로 줄이는 거죠. 네. 그래서 이렇게 만드는 게 왜 좋냐? 뭐 똑같은 계산은 왜 이렇게 뭐 쓸데없이 매트릭스랑 벡터의 곱으로 나타내느냐? 저렇게 해서 코드를 맷머리든 뭐 이런 식으로 짜두면 그러면 이제 GPU가 저거를 싹 다 패러렐라이즈를 해준다는 거죠. 네. 근데 사실 뭐 이 포룹을 패러렐라이즈를 할 수도 있어요. 뭐 코드상으로도 이제 뭐 패러렐 for loop 같은 거 지원하는 또 이제 패러렐 그 프로그래밍 라이브러리들이 있기는 있어요. 그래서 저게 이제 패러렐라이즈가 가능하니까 이제 그걸 내가 이제 일일이 다 패러렐라이즈를 하자. 근데 그렇게 되면은 좀 고라파지고 이제 왜냐면 이게 우리가 항상 그 뭐 통신도 그렇지만 이제 OSI 7레이어 뭐 이런 거 있잖아요. 그게 뭔가 이제 아래쪽에서 하는 일을 약간 왼손이 하는 일을 오른손이 모르게 하라 뭐 이런 거 있잖아요. 그러니까 아래쪽에서 뭐가 일어나는지 이제 내가 모른 채 이제 위쪽에서 내가 그걸 앱스트랙션 해갖고 나는 그 위쪽에서의 뭔가 오퍼레이션만 집중을 하면 네. 아래쪽에서 어떤 이게 이럴 때는 저게 아래쪽에서 이런 거 신경 쓰기 시작하면 내가 할 수 있는 고차원적인 뭔가 일을 못 한단 말이죠. 뭐 하여튼 그래서 이제 그런 이제 앱스트랙션이 이렇게 쭉 진행이 되잖아요. 역시 이것도 마찬가지예요. 그러니까 이것도 이제 뭐 이 특정한 케이스에 대해서는 패러렐라이즈를 그 아랫단에서 이제 GPU까지 내려가서 이제 할 수도 있겠지만 이제 그것까지 신경 쓰자면 이제 뭐 사실 어떻게 보면 좀 너무 한도 끝도 없고 이제 GPU가 아랫단에서 그 쿠다라고 이루어지는 뭐 C-like한 그러니까 C와 비슷한 형태의 이제 그 GPU 프로그래밍 라이브러리가 있고 거기서 이제 굉장히 이제 그런 매트릭스 멀티플리케이션 맨멀 펑션이 딱 들어왔다. 그럼 그거는 내부적으로 싹 다 패러렐라이즈 하도록 이렇게 펑션이 다 이렇게 라이브러리가 잘 되어 있고 우리는 이제 이 윗단에서만 노는 거예요. 그러면 이제 저 매트릭스 멀티플리케이션으로 만들어주면 저게 이제 내부적으로는 이제 자동으로 이제 패러렐라이즈가 되니까 이제 그런 이점을 우리가 살릴 수가 있다는 거죠. 근데 그렇게 하려면 기본적으로 이런 지금 얘기했던 매트릭스 혹은 매트릭스 벡터 멀티플리케이션을 만들어줘야 되고 그렇게 만들려면 이 매트릭스를 실제로 만드는 과정에서 이제 메모리에 이제 중복이 이제 끼어든다는 거죠. 네. 또 다른 질문 있나요? Okay, so now let me describe why the deconvolution is called transposed conv. Okay, so from this perspective, let's see. Okay, so you guys understand this this process as the deconvolution, right? And then here, the activation map can be viewed as this guy, X, Y, Z, and 0, 0. I mean, I'm just rewriting this computation in this form. X, Y, Z, and 0, 0, and 0, 0, and X, Y, Z, right? Okay, and so it is multiplied with the scalar A and scalar B, right? So it is like, so we just multiply A with this each of our filter element values, and then we put it into the corresponding position, right? And then for the second value of an input activation map, input activation value, and then apply the scalar multiple, and then we put it in the corresponding position, right? And then if we consider the entire size of an output activation map, and then we just simply add this zero padding so that this entire vector is now corresponding to the output activation map, okay? And then XYZ and XYZ, those different positions are filled by our filter coefficient, and then we multiply it with this scalar multiple that came from our input activation value, right? Okay, so in this case, now it can be viewed as this guy. You guys know that it is a linear combination of these two columns with the coefficient as A and B, and then we can now utilize this as so I'll use this A and B, and XYZ 0 0 0 0 0 XYZ. Okay, so we can factor this representation into this matrix and vector multiplication, right? And so it is simply just a linear combination of these two columns on the left, right? And so now it can be viewed as like this kind of IM2 Kuocw kind of thing, right? Just like this. So on the left, on the right, we have our input activation map, right? And then on the right, we now have like a padded version, or this expanded or enlarged version of our filter coefficient, right? By filling or padding all the zeros in the irrelevant part, right? Okay, so so that way it can be viewed almost similar to this kind of process, right? So what's the difference between this and this part? So in this case, because we needed the inner product, so these are input activation map, and then we needed to do the linear combination with our filter coefficient, right? And then produce a single output. Okay, the single output. So in this case, this kind of convolution can be viewed as this row vector times column vector to produce single scalar value. But in the case of deconvolution, we now think of it as the scalar multiple of this guy with this column vector that is defined as our filter coefficient. Okay. So that way, if we compare this guy and this guy, so now this is our normal or original conv, but in the case of deconv, if this was our filter coefficient, and then we, rather than placing it as a row vector, we place it as a column vector, so that we can perform the scalar multiple with the input activation value. So that way, roughly this guy is, if this guy is transposed, and then our convolution filter is now a column vector, right? Column vector rather than a row vector. So that's why we call it as transposed conv, because we just transpose this part from our normal conv operation to obtain this deconv operation. Any questions? 다 이해가죠? Okay, so this was a 1D case But if we extend it, what if we use the 2D conv or 2D deconv? Okay, so in that case, I mean, the overall process is almost the same. So in the case of 2D conv, like, so we have this input activation map, for example, like this, and then suppose our filter size is only having a 2x2, right? So in this case, we just rearrange or reshape this 2D activation map into this form. So we have one vector, and then another vector, and then concatenate it into the bottom part, so that we obtain this long and thin column vector. So that can be viewed as a single single input activation map represented as a single vector. Okay, and then suppose we have 1, 2, 3, 4 as our filter coefficient. Okay, and then what will be the first conv output, or first activation map output? And then so we have it's too large. So let's consider like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then if we form it as a single column vector, then this one will be our column vector, and then 10, 11, 12, and 4, 13. And then what will be the corresponding row vector to form our matrix on the left? It will be 10, 11, because these two will be multiplied with these guys, right? No, it should be 12 over here, right? Because 1 times 10 and 2 times 12, right? So here we have a 12, and what's the corresponding coefficient for this 3 input activation value? And then it should be 0, right? And then 4 is matching with the 11, right? 11 and 13 and all the zeros, right? You get the idea? So this is how we can rearrange the 2D conv as this a single matrix vector multiplication, and then using the same idea we can implement the deconv operation. Any questions so far? Okay. Then next I want to discuss about something called the checkerboard effect of this deconvolution. So in this particular case, as you can see, we see some kind of an overlap between these two kind of scalar multiple of our filters, right? So if our step size is strictly less than the filter size, and then we inevitably have the overlapping parts, right? And then in general, in this case, this pixel value, and also if we imagine doing one additional kind of activation map, so if we have an additional input activation value, and then the third vector will be placed over here, right? And so these parts, the pixel values and the output activation map will be the sum of these two parts, but in this case they will be just a single output of the single activation map. Okay, so so this is known as this checkerboard artifact. So this is a deconv having the filter size as 3 by 3 and the step size as 2. Okay, so in this case, roughly the image size will be expanded or enlarged by the ratio of 2, right? And then Now, in this part, yeah, you can see that this darker part is the overlapping region where those two outputs from this the decomp operation from two different locations is added together, right? And sometimes in this part, yeah, so those even darker part will be formed as the sum of the four different values, right? So in that case, in general, if we just assume our filter coefficient of like this 3x3 filters as a kind of random variable having the same mean and the variance, for example, and then those darker part will have larger variance, right? Because it will be the sum of more number of random variables, right? So that way, we sometimes see this kind of checkerboard pattern in our decomp output, like this kind of some regular. It is a little bit hard to see, but yeah. Let's see. Okay, so in this case, you can roughly see this kind of checkerboard pattern where, this with the same interval, we see a little bit, relatively darker pixels than the other pixels. Okay. Okay, so there are several techniques that can, they can kind of avoid, they can prevent this kind of, undesirable effect. Okay, but you can, understand this as a general kind of drawback or disadvantage of using deconvolution in order to increase the spatial resolution in our decoder part. Any questions? Okay. So I'd like to briefly discuss this fully convolutional network. Fully convolutional network. Did I explain this fully convolutional network? Okay, so in short, it is of course called the FCN, fully convolutional network, but it is not actually fully connected network. It's actually fully convolutional network. Okay, so in this case, the main idea is quite interesting. So you now change all the operation. I mean, basically the main trick is to change the fully connected layer into the convolution operation. Okay, so in this case of a VGG network or this Google Net, let's see. So at some point in our VGG network or in general any other image classification networks like resonance and denseness and so on. So starting from some point, we now change the phase into the fully connected layer instead of convolution layer, right? So in this part, we obtained this kind of output activation map, and then we just reshape it into a long column vector, and then start with our fully connected layer, right? And then so over here, starting from here, the first fully connected layer will have the output node output dimension as 4096, right? So in this particular case, let me just ask one question of. Okay, so typically when performing this image classification, the input image size should be fixed as that, right? 224 and 224 by 3. But what if we just what if we feed a larger size of an image? Sometimes some images are some images are taken as a photo with the low resolution, but some other photos will have a higher resolution, right? So in this case, our image size is, for example, 300 by 300 by 3. Okay, so it's just one example of a larger size of an image. So in this case, you just assume just feed forward or just feed it to our VGG network, and then when exactly will our error occur? Okay, so during all these convolution and the pooling layer, will it make any error message over here? It will not, right? Because given the larger activation map size, okay, and then we will just do the combo operation, and then the output activation map could be just could be larger than usual, correspondingly, right? Again, if we have a larger input image size or larger input activation map size, and then the combo operation has no problem of obtaining or producing the corresponding output activation map, right? But when is it? Yeah, when is this error happening exactly? That is when we just turn to this fully connected layer, because this fully connected layer in the middle, between here, it will take the exact same number of an output as this guy, as number of an input node as this value. But in this case, okay, give me 1 second. It doesn't work. Okay. Okay, so at this point, because we fed a larger input image size from the beginning over here, and then suppose we obtained larger activation map size at this point. So for example, our input activation map is this guy, 10 by 10 by 512. But in this fully connected layer is assuming that the exact same number of an input nodes, same as this guy, right? So we cannot fit this guy into this fully connected layer, right? So that's an obvious phenomenon, right? But in order to handle this situation, motivated by this, we can actually change all the fully connected layer as a kind of a special case of a conf. Okay, special case of a conf. So how do we do? How do we do that? So in this case, okay, so suppose we have this activation map, and then now we turn to the fully connected layer, and then it will be just reshaped into this a single vector, having a 4-dimensional vector, and then now we have, suppose we have a 2-dimensional output in this fully connected layer, and then okay, so for this y1 and y2, and then suppose y1 is this x1, x2, x3, x4, and y1 is represented as x1, 2x2, 3x3, and 4x4. Suppose that is our fully connected layer like parameters that we learned. Okay, so in this case, so this guy is like 5x1, 6x2, 7x3 plus 8x4. So in this case, how about just changing it into conv, so that we have the first convolution layer as like 1, 2, 3, 4. Okay, so here our filter size is exactly the same as input activation map. Okay, and then since our filter size is the same as an input activation map, there is no kind of a room for moving around, right? So in this case, it will just produce a single output activation map, right? And that will correspond to this value. And then now the second filter output is 5, 6, 7, 8. And then applying this filter into this, and then we obtain the single, single output activation map. And then we concatenate that, and then we obtain it. Okay. Okay, so in this case, the fully connected layer can be viewed as this a special case of this convolution layer, where the filter size, I mean each of our filter is exactly the same size as the input activation map. And how many number of filters do we have? How many filters do we have? Filter size will be exactly the same as the output node in the original fully connected layer, right? Because one convolution filter will produce one single output, right? Because that is exactly fitting, matching with the input image, right? With the no room for moving around. Okay, so that way we can just change every convolution layer over here as a single, as a convolutional layer. Every fully connected layer into convolution layer. So in this case, so if we had this activation map as an input, and then what will be the difference in this case? Okay, so now, we have larger input activation map. Okay, unlike the typical situation. So we just gave the strange or larger kind of relatively large input image, and then at this particular point, and then we will have this large input activation map at that particular layer. Okay, so in this case, if we were to have this normal input activation map size, and then it will produce a single output. But now it is defined as a conv like this, and then given this larger activation map size, and then we now have a room for moving around our filters like this. Okay, so applying one single convolution filter will now produce like 4 different outputs instead of a single output. Okay, so now for the second filter, and then we will obtain another activation map size that has no longer the spatial resolution as 1 by 1, which is a kind of a larger size than this 1 by 1 spatial resolution. Okay, and then now let's just imagine we arrived at this node. Okay, at this final node. So in that final node, and then typically we will obtain the spatial resolution as 1 by 1, and then the dimension will be 1000, where each of them is corresponding to our particular class or category in this object classification, right? And then given this 1000 dimensional vector, using it as a logit value, and then we apply it. We apply it to the softmax layer to obtain the single distribution across or over this 1000 different class categories, right? But now if we just have a larger spatial size, larger spatial resolution like this, okay, and then instead of using a single 1 by 1 spatial resolution, we now have like 4 by 4 and 1000 as our channel size or depth. Okay, so in this case, how can we apply the softmax over here? So we need to give a single high dimensional vector as an input to the softmax layer. But here, how can we apply the softmax over here? And then the softmax is applied at every different location of 1000 dimensional vector. Okay, and then this intuitively the meaning of this 1000 dimensional vector at a different position is indicating the logit value of the likelihood of a particular category at that particular position. Okay, so if we have a single 224 by 220 image, and then at the fully connected layer and all the way at the end of this softmax layer. And then we obtain the 1x1 spatial resolution and then 1000-dimensional vector. So that will summarize, or that will describe the entire image level class distribution or probability distribution across different categories. But in this particular case, because we gave a larger size of an input image, and then the output, the final output will have some, more size of the activation map. I mean, that has the spatial resolution more than 1x1, and then still at each position we have a 1000-dimensional vector, and that vector is describing the probability of a particular, of different classes at that particular position and over here. Okay, so in this case, it's like given this 300 by 300 images, and then once we obtain this 2x2, and then it's roughly saying that, okay, this part is likely to be like dog, but this part is likely to be like, some other, maybe cat and so on. And then how can we obtain, but still in this case, we want to obtain the single kind of image level class prediction. So we want to be able to say that, okay, this image is predicted as a cat, right? Rather than like specifying different categories or different classes per different locations, right? So in this case, we typically have global average pooling at this logit value. So in this case, we have the global average pooling to obtain a 1x1 by 1000, for example, logit value. Okay. So this is how we can kind of change this fully connected layer into like fully convolutional layer, because we no longer have any other layers like we don't have any fully connected layer, but all the layers were replaced by the fully convolutional layer. Although we have the max pooling and so on, but at least we don't have any fully connected layer, and thus once we change that, and then even if we gave the larger size of an input image, and then it will have it will have no errors when running this code. Any questions? 네. Okay, so the time's up. So, Okay, then let's continue to discuss on the remaining chapter and the next chapter, and also some other topics in this Wednesday. Okay, thank you.